Ellipse is a set of all points whose distances for two focus points. So F1 and F2 are focus points called the foci. So we're talking about ellipse. Again, it's a type of conic. This definition isn't going to make a lot of sense just reading it. So let's try to show it to you and maybe it'll make sense. So if you could picture this as, do you see those two focus points like F1 and F2 there? Imagine those are like pin tacks on your piece of paper. You might have done something like this in geometry potentially. And imagine that dotted line there is a string. So it's a string that goes from focus point to a point on the ellipse to the other focus point. So it's a constant length. The sum of whose distances is constant. So that string is one length, and I'm holding it taut. Pretend this P point is a pencil, that I'm holding it taut so that it stays kind of in a straight line there, that piece of string. So if I move this point, the string remains the same length. In fact, the string is 15.62, this particular string is. But the distances change, right? The distances between that point and that point are different now, but it's still the same string, the same constant distance. If I move this all around and the string stays the same length, 15.62 no matter where I move it, every point on this figure, called an ellipse, would be equidistant, like the string is the same length the whole time. And so that forms the ellipse. Now, we don't actually draw an ellipse that way, but that's the definition of an ellipse. And so that's why we bother to, where are the focus points at? Just a general thing which may help you. If an ellipse is really squished, like if it's really, kind of, it'll have the major axis. We'll talk about that in a minute. But the focus points will be right towards the end of that. You'll always have two focus points on the ellipse. They'll be right towards the end of that kind of really squished ellipse. If you have something that's more circular, in fact, if it was entirely circular, that would be one of the focus points, and this would be the other focus point. They'd be on top of each other. If it's perfectly circular, the focus points would be more towards the center. As a general rule of thumb. That might help you sometimes when you're kind of estimating things. So let's figure out all the formulas here. So this is the basic formula for ellipse. I should say for ellipse with the center at the origin at 0, 0. Right, so if the center is at these are all the formulas. They're going to change slightly later in the chapter when we have this might have an x minus h squared, this might have a y minus h squared, k squared, but the rest of it will be about the same. So it'll be similar, but a little bit different. But they're equal to 1 here, this formula. It's kind of interesting. So this, let's talk about the figure first here. So the distance from this point to that point is the major axis. You can tell this is a horizontal ellipse. I think it was called a horizontal ellipse. This point right here is called the vertex, and this point right here are the vertex. So again, the major axis there is the horizontal axis because it's longer than it is tall here. The minor axis in this case, the shorter axis, the smaller axis goes from this point to this point. And those points are technically called, this point and this point are called co-vertices. Co-vertices. We don't really refer to that name very often, but it's nice to know. The main vertex there are on the major axis. So in this case, it's horizontal. These points right here, this would be a focus point. You can call that F1 if you wanted to, and we call this F2, just to designate that they're different points there. The distance that those points are away, so this distance from the focus to the center is a distance of c. Same thing this way, so you can write this on your paper. I'll allow you this on the formula sheet as well. The distance from the vertex to the center, from here to here, is a distance of a. So a is always larger than c for an ellipse. That's always true. And the distance from the center of the vertex is also called a. So really, you have the distances here. So major axis would be A plus A, which is 2A. And then in the other direction, from the co-vertice to the center, that distance is called B. That half of the minor axis is B, and the other half of the minor axis is also B. So this is equal to 2B. 2B turned out to be. The focus points already labeled there. They're plus or minus C, 0. And the vertices are already labeled there, plus or minus A, 0. Those are two different points, but I just kind of shortcutted it. This formula is always true for an ellipse. Be careful when we get to hyperbolas, that'll be a slightly different formula. This is saying two things. It's saying A and B are always both positive. A, B, and C are always positive, actually. They're distances. But A is always bigger than B, which kind of makes sense, because remember, A is part of the longer major axis, half the major axis, whereas B is half the minor shorter axis. So it's always longer than B. And there's one more thing I wanted to point out. So I don't have it on here, but I think it's on here. So we'll learn about it in a minute. It's called eccentricity. You might as well put it as one of your formulas. So eccentricity, which is equal to C over A, I believe. Let's see, C over A. Yes, that's true. And we'll get to that in a minute. Vertical ellipses. So these are the formulas for a vertical ellipse. So let's start with the major axis. Whoops. Let me do a different color just to keep it consistent. Okay, so the major axis goes from vertex to vertex. It's the major one. You may notice, like, well, let me get to that in a minute. Minor axis. Right there. I didn't mention this earlier, but this is what's changed. So from the horizontal to vertical ellipse formula, the A and B are switched. So it's vertical, which means the longer value A is underneath the vertical y-axis, whereas in the other formula, X was horizontal, so the bigger value A squared, is below the X term, which X is horizontal movement, Y is vertical movement. So sometimes it helps to easily remember which one's which. So this point is the vertex point. This point down here is the other vertex. These would be co-vertices, part of the minor axis. The distance from the center to the vertex would be called A. The distance from the center to the co-vertice is called B. And the distance from the center to the focus point is called C. And that's the focus right there. And that's the focus right there. So it's helpful to have this picture for your formula sheet so you can kind of identify the A, B, and C. Usually we're given kind of A and B, or A and C, or C and B, and we can figure out the others using this formula, right? If you know two of the three, it's almost the Pythagorean theorem. It's not quite. A squared is almost like the hypotenuse there, but if you're given two of them, you can usually figure out the third. This formula is the same, so it's 2A. This one's 2B. These points are a little bit different. You notice the focus points are, instead of plus or minus C, 0, it's 0, plus or minus C. Again, these are both for origin is the center, and this is 0, plus or minus A. And again, that formula there in the top left is saying the same, top left is saying the same thing. A and B and C are both positive, and A is always bigger than B, so that's always true. And that's your main formula for the ellipse that we have to figure out, basically A and B, to write the formula. Okay, eccentricity is C over A for both types. It's just a ratio. It actually can be, so let's see, can it be 0? I think let's think about a circle. So eccentricity could be 0 actually. So I think that's actually true. So if C over A, so if in this case, remember the center, the focus points are both there. So the distance from the center to the focus point is 0. So it'd be C would be 0. So it'd be 0 over some value for A, and that would be equal to 0. So it can actually technically, if it's a circle, it can be equal to 0. So the smaller eccentricity is, or closer to 0, the more circular it is, if that makes sense. This one's just a little bit squished, it's 0.52. This one looks pretty squished, so it's 0.87. So I guess it could go to 0.9 something, that'd be really squished, right? So just in general, that's what, it's a measure of how squished the circle is what eccentricity is. 1 means it's, or close to 1 would be it's really squished, and close to 0 would be it's not very squished. Planets actually move in elliptical orbits. The sun is the focus. It's interesting because there's only, there's no focus over here, right there, where you'd expect one, but sun is the focus of the elliptical orbit. So that's kind of interesting. But these are the different eccentricities, right? So which one is the most circular orbit here of all of them? And so the most circular orbit would be the Venus, right? Because it's not quite a circle, straight circle, but it's just a little bit squished, not very much. And I don't know if you consider Pluto a planet, but it has the most squished. So its orbit is more squished, kind of a elliptical, like what we think of an elliptical type of orbit, where it's 0.25. So, and then this is like the Perihelion Ephelian. So what's interesting is, the Earth moves around the sun, where the sun is the focus point. And you would think, I think this is, in the wintertime, United States is over here, which we're actually closer to the sun. And so you'd think wintertime would be, I guess, the hotter season. But because of the tilt of the Earth and how much sun we get, even though the Earth is closer to the sun, I think that's the way it works, that because of our tilt and our orbit, we don't get as much sun. Just a side note about all that. But we use that sometimes with astronomy. So given this, find this. So you may notice the formula, like both formulas, kind of equal to 1 here, right? And this formula clearly doesn't equal 1. I don't like that. So we have to make it equal to 1. So this is kind of a neat move we do. So we just divide by whatever that number is. And so we're going to divide by 36 in this case. And it should simplify pretty nicely here. So this equals 1. I like that. 9 over 36 is like 1 over 4. So this ends up being y squared over 4. And that of that 1 over 9, that simplifies, so x squared over 9. Now this thing is in exactly the right form. So I'm very happy with the form of that. So you can be a formula person and just start plotting use the formulas and figure it out. The big thing here is that the a squared value, a squared is the bigger term, a squared or b squared, which one's which, right? So this one has to be a squared equals 9 because 9 is the bigger number, right? So a would have to equal 3. And this number would have to be the b squared term because it's a smaller, so b squared equals 4, so b equals 2. And so the way I do this is I just go, okay, a is 3, right? So it's underneath x. X is always horizontal movement, right and left. So I'm going to start at the center, which is 0, 0. I'm going to go 3 to the right and 3 to the left to make my 2 points for the ellipse. Y is vertical movement, so b is 2. So I'm going to go up 2 to the covertice, down 2 to the covertice, and I'm going to draw my beautiful ellipse. So that's the fast way of doing this. It'll really help you if you start doing this way for ellipses and hyperbolas, actually. It just makes it so much faster and easier to do. You might want to identify just for yourself, like which one's the major axis. So that one's the major axis, which means somewhere on there are going to be the 2 focus points, right? A distance of c away from the center. because that distance of c away from the center. So what I would consider doing at this point is maybe using that formula. I think it was, let's look back on that. So for both of them, the formula is c squared equals a squared minus b squared. Remember, the distance from the focus point to the center is c. So if I can figure out c using that formula, I can then figure out how far away the focus point is from the center there. So c squared equals a squared minus b squared. I have trouble memorizing that. By the way, you're not going to have to memorize these, right? I'll give you a formula sheet. So c squared equals a squared minus b squared. So I'm just going to plug in my a and b there. So c squared, a squared, I think was 9. B squared was 4. So c squared equals 5. So c equals the square root of 5. I don't have to worry about the negative case here, only the positive. So when I take the square root of both sides. So c is approximately equal to plus, let's see, 1 point, I don't know, 1.6 or something there. I'm not sure exactly, 1 point something. Because, no, square root of 5. Let's just do that for a second in a calculator. Sorry. So you get your scratch pad out, square root of 5, and press enter. 2.23. Sorry, had to be over 2. So 2.23 is approximately 2.2. So 2.2. So I'm going to go 2.2 to the right. Make a focus point. It's pretty squished. It's kind of towards the end, and 2.2 to the left. And make a focus point. So those are my 2 focus points. I would want to label those using the formula. Again, the formula is, I think it's plus or minus c, comma 0. So I'm going to use the exact value when I write the formula here. So it's going to be plus or minus square root of 5, comma 0 are the ordered pairs of those points. The vertexes, you might just be able to look at them, or you could use the formula. The formula is plus or minus a. Again, the formulas kind of help you label things. Plus or minus 3, comma 0, because a is 3, right? And so we don't really, we didn't really need the formula because we saw the points are at 3, 0 and negative 3, 0. The length of the major axis, we want to define that, would be 2 times a, so 2 times 3, which would be 6. Length of the minor axis is equal to 2 times b, which is 2, I believe. B was 2 right there. And so that'd be 4. That's just how long that is. From there to there is 4. From there to there is 6. And finally, eccentricity is c over a. And so c over a would be square root of 5 over a, which is 3. And so we can actually, this is the measure of how squished that is. So we could just divide by 5 there, because that's square root of 5, 0.447. So that's equal to 0.447. So it's, pretty squished there. Okay, this is a tough one. So I wanted to do a tough one because it doesn't get really much tougher than this for ellipses. So divide by 25, similar to what we did last time. It's not going to work out as well. You'll see. So we get this is nice, equals 1. I like the y term, y squared over, we want y squared over a number. It's y squared over 25. And this one didn't work out as well. I really want x squared over a number, and there's a fraction there that doesn't simplify. Like the other one, 4 over, it just worked out nicely, like 4 over 36 or stuff like that. This one doesn't simplify, so you actually have to have a fraction down there. Some of you may get this. I actually have a few people in every class who go, oh, I know what the fraction would be. It would be 25 over 16. Because you divide by a fraction, you multiply by its reciprocal. So you can see those two things are equivalent when you multiply by the reciprocal. Oh, 16/25. So it's important to write that all as in the denominator. So that's why we use the fraction there rather than just leaving it 16/25. The form is x squared over either a squared or b squared. Hopefully you see the bigger number is definitely 25 here. That's only a little bit more than 1. That's 25. So you can tell which one is your a squared and which one is your b squared. So this one is my a squared. So that's going to be a equals 5. This one is my b squared. So b squared is this. So my b is equal to the square root of that, which is 5/4, or 1.25. So a is 5, so a is underneath y, which is vertical movement. So I'm going to start at my center, which is 0, 0. I'm going to go up 5 and down 5. That's vertical movement because it's underneath y. X is horizontal movement, so that's going right and left at 5/4. So 1 1/4 are right about there-ish. 1 1/4 in the other direction, right about there. So you can see this is a very squished ellipse. Eccentricity is going to be close to 1. And we've got it. The major axis is the longer axis there. So that would be this one from vertex to vertex. The shorter one would be the minor axis from covertice to covertice. And somewhere in there are the distance of C away. Probably very close to there as the focus points, but we'll get to that in a minute. Let's go ahead and figure out the focus points. So C squared, if I remember the formula, A squared minus B squared. You might need a calculator for this section because it's got a lot of, so that'd be what, 25/16. So C squared, and the reason is because we've got to convert this to, 16 times 25 over 16. So I'm just going to type that in. So 25 minus 25/16, I think. 375/16. So we get 375/16 is C squared. We take the square root of both sides. We get C equals, that's going to be 4 down there, and that's a square root of 375, which I think does simplify. 25 is a perfect square. 25 goes into that 15 times. So that would be 5√15 over 4. This is the exact value of C, right? 5√15 over 4, so 5√15 divided by 4. Put a decimal point in there, so it gives me a decimal answer. It is 4.84. I need that for graphing purposes. So C is approximately equal to 4.8-ish. So 4.8 up is my focus point right there, and 4.8 down is my focus point. Those are my focus points, very close to there because it's very squished. But when I write it, I want to write it using the formula, so 0, plus or minus C, so 5 plus or minus 5√15 over 4. The vertices are much easier. You can just see them. They're 0 plus or minus 5. The formula is plus or minus A, which is 5. The length of the major axis would be 2 times A, 2 times 5, which is 10. Length of the minor axis would be 2 times B, which is 5/4, which is 10/4, which is the 2 that cancels, so we get 5/2, or 2.5 is the length of the minor, and then C over A is our eccentricity. So that would be 5√15 over 4 in the numerator. And then in the denominator would be A, which is 5. So I'm just going to divide that number we had in there by 5. We get 0.968. Wow, so pretty big eccentricity. 968 is very close to 1, so it's very squished, so to speak. It's a great math term, right? And that's how to graph ellipses. So let's go back since that's about it, I think, for today. That's enough.